Welcome to the History of Astronomy module. First things first, why should we spend any time whatsoever on the history of astronomy? Who really cares about Aristarchus or Copernicus in the 21st century anyway? Why not get right into Newton's laws, exoplanets, dark energy, leaving history for other courses? It's important to spend one lecture on the history of astronomy fundamentally because it's important for any discipline to know where it came from, to better appreciate where it's at and where it's going. Sounds trite, but it's true. More relevant for you, however, is that while most texts do touch upon the history of astronomy, their treatment is often incomplete and sometimes misrepresents what actually transpired, particularly when it comes to the scientific revolution. As a university student, everything you study should reflect top-notch scholarship. The purpose of this module is to introduce and discuss the evolution of astronomy, at least up until the end of the 17th century when the scientific revolution was established. So let's begin with prehistory. Astronomy has been called the oldest of the sciences, at least by astronomers. Human beings of all cultures have been acutely aware of the nature and rhythms of the day and night skies for thousands of years. Megalithic or massive stone structures such as Newgrange in Ireland and Stonehenge in England, as you see on this slide, demonstrate that prehistoric people already had a sophisticated understanding of celestial rhythms. They were well aware of the dates of the solstices, the first days of summer and winter when the sun stood still in the sky. Major ancient cultures developed reasonably accurate calendars, from the Sumerians, Babylonians, and Chinese to the Mayans in Mesoamerica and the Islamic culture in the Middle East. Moreover, all ancient cultures linked patterns of stars in the sky, what we call constellations, to specific cultural myths and legends. This was driven in part because astronomy had practical applications. Timekeeping was of vital importance for critical activities such as agriculture, when to plant, when to harvest, and knowledge of positional astronomy became essential for navigation purposes, particularly for seafaring cultures. In addition, there was a strong link between astronomy and astrology that was only broken well after the dawn of the scientific revolution. The next stage in the evolution of astronomy took place in ancient Greece. As far as we are aware, curiosity has always been an essential characteristic of human beings. We have always sought explanations for natural phenomena. Science comes from the Latin scientia, which means knowledge. Humans have always exhibited a thirst for knowledge, a passion for truth. Most cultures in history were largely content to understand events in the natural world using narratives or stories that relied on myths, often religious in character. For example, the Sumerian creation story, Eridogenesis, or the Norse explanation for thunder as the motion of Thor's chariot. But about 2,500 years ago in ancient Greece, philosophers, lovers of wisdom, began to seek explanations of phenomena based on observations of the natural world alone. Thus began a rudimentary practice of science that emerged in full flower nearly 2,000 years later in Western Europe. Why did this happen in ancient Greece? The answer is apparently rather complex. The ancient Greeks had developed an underlying philosophy that encouraged the answering of how questions, without an appeal to myths, using only observations of the natural world. Their level of mathematics was also sufficient to allow them to construct and compare quantitative models. Many ancient Greeks made significant contributions to physics and astronomy. Among the most influential from our perspective lived in the 2nd and 3rd centuries BC or BCE. They were Aristarchus, Eratosthenes, Hipparchus, and later Ptolemy. Aristarchus of Samos. Before him, philosophers believed that Earth was at the center of the universe. That is, they believed in a geocentric model of the universe, geos, Earth. Aristarchus was among the first to propose a heliocentric, that is, sun-centered model for the universe, helios, sun. There was no distinction at the time between the universe and the solar system, of course. The second was Eratosthenes of Cyrene. He not only proposed that Earth was round, but he calculated its circumference to reasonable accuracy using simple geometry. As in a previous module, you've heard that the lengths of shadows cast by vertical structures at different latitudes at the same moment could be used to estimate Earth's circumference. Hipparchus of Nicaea. Hipparchus is among the greatest astronomers of antiquity. Among other contributions, he produced accurate star maps and catalogs for nearly 1,000 stars, and discovered precession, the slow change in the position of Earth's rotation axis on the sky. The world had to wait over 1,700 years before more reliable maps became available. Claudius Ptolemy of Alexandria. In the 2nd century AD, or CE, Ptolemy developed the most sophisticated and accurate geocentric model for the universe, a model that was employed for the next 1,500 years. Ancient Greece also gave rise to many brilliant philosophers, including Plato and Aristotle, whose influence can still be felt today. Aristotle is considered to be among the greatest minds in history. He made substantial contributions to many disciplines, including physics and astronomy, in the 4th century BC, or BCE. Aristotle's views in physics held sway for over 1,700 years following the decline of the Greek Empire, the rise of the Roman Empire, and throughout the Middle Ages. Aristotle's laws of physics are summarized in the next slide, side by side with Newton's laws. It's important to note that Aristotle's laws are based on common sense. Shouldn't heavier objects fall faster than lighter objects? Doesn't a moving object require an applied force even if it's moving at a constant speed? No, and no, as you know, or will know, as you proceed with the study of Newton's laws in your physics and astronomy courses. Here we have Aristotle's and Newton's equivalent laws side by side for comparison. For example, Aristotle said that objects that move with a constant or any velocity require an applied force. Not so, said Newton, of course, in his laws, that an applied force leads to an acceleration. A constant velocity does not require a force. Aristotle suggested heavier objects fall faster than lighter objects. Newton said objects of all masses fall at the same rate. Aristotle suggested that objects tend to seek their natural place and come to rest at the center of the universe. Since objects appear to come to rest on Earth, ergo, Earth must be the geographical center of the universe. Newton, those in the scientific revolution, suggested the scientific method applies only to the natural world and should not invoke purpose or final causes. Aristotle held that planetary orbits must be circular because circular orbits are perfect. infinite number of degrees of symmetry or symmetry axes, and of course the creator would only make something that was perfect. Notice these are non-natural illusions or axioms in the model. Whereas Newton demonstrated the truth of Kepler's laws, which we'll examine shortly, that planetary orbits are ellipses, and these follow, of course, directly from the law of universal gravitation. So, why the difference? Aristotle's laws were not subject to experimental verification. That's not something Greek philosophers were normally concerned with. His laws also involve certain assumptions or axioms related to the nature and purpose of an object that influence its motion. Assumptions, as we've seen, that modern science would reject. Aristotle's laws, however, were common sense, right? As physicists, we must always be wary of arguments from common sense, even arguments by the great Aristotle. It is important to pause here to pose a few critical questions. Why did most Greek philosophers, not to mention scholars in the Roman Empire and throughout Europe in the Middle Ages, reject Aristarchus's heliocentric model for a geocentric model? We now know Aristarchus was right after all. Scholars at the time were well aware that if Earth revolved about the sun as proposed by Aristarchus, then at least some stars should exhibit parallax, an apparent shift of nearby stars relative to the more distant stars as Earth traveled around the sun in an orbit. You have here on the bottom right portion of this slide a schematic showing that as Earth moved about the sun, then the nearby stars would seem to shift slightly with respect to the more distant stars. The best naked eye observations, however, did not reveal any stellar parallax. Furthermore, most scholars at the time believed that stars were at most millions of kilometers, in today's units, away, based on other arguments, and so should have detectable parallaxes. So this provided strong evidence that Earth was not in motion relative to the stars and therefore occupied the center of the universe. Before we get too critical of the ancients, it wasn't until the 19th century that the first stellar parallax was detected using telescopes and sophisticated measurement techniques. This showed that stars were at least millions of times further away than the ancients imagined, explaining their failure to measure stellar parallax. Why did most scholars reject the hypothesis of a round Earth until Columbus proved differently in the late 15th century? This is one of the great historical misconceptions in popular culture. In fact, the concept of a round or spherical Earth was already widespread at the time of Eratosthenes, though Eratosthenes did calculate its circumference to reasonable accuracy, as we've discovered. And scholars throughout the Middle Ages believed Earth to be round. This misconception was introduced into popular culture in the 19th century, where it has stubbornly resided ever since. This myth survives in part because modernity, with its strong commitment to science, is eager to accept any claim of superiority over an earlier and therefore less enlightened era. And finally, on to the third stage, the scientific revolution. The next major advance in astronomy didn't occur until the dawn of the scientific revolution in the 15th and 16th centuries. Why did science go dark for 1500 years during the Roman Empire and Middle Ages? Well, it's incorrect to say that our understanding of the natural world stagnated for 1500 years. The Romans did make considerable progress in engineering and what we would call today applied science. Witness their bridges and aqueducts, as well as advances in military technology. Contemplating the natural world using scientific models was just not their focus. The Middle Ages followed the Roman Empire from about the 4th century until the Renaissance or rebirth in the 14th century. Contrary to some popular accounts, the Middle Ages were not the Dark Ages. What is the case, however, is that scholars at the time were largely content to answer the how questions using religious narratives, since the culture was more concerned with how to get to heaven than how the heavens go, with apologies to Galileo. It is at this point that most introductory astronomy texts provide a confusing and largely incomplete account of the birth of what is called the scientific revolution that began with Copernicus in the 15th century and continued until at least Newton in the late 17th century. References usually portray this revolution as a blitzkrieg, a lightning war, in which the superstition of religion was overthrown by the rise of an unstoppable tide of rationality, ultimately leading to the Enlightenment and the triumph of human reason. The actual story, however, is a great deal more complicated. Modern science is based on a method, the scientific method. Who is responsible for the modern scientific method? Well, some thinkers such as the Muslim Ibn al-Haytham at the end of the first millennium promoted the basic elements of what came to be called the scientific method. It was scholastic theologians such as Father Roger Bacon in the 13th and 14th centuries who developed the modern scientific method. These theologians reckoned that by searching for truths and laws in the natural world, one might achieve a greater understanding of the ultimate truth and lawgiver, whom they called God. The scientific method is without doubt the most successful method of discovering truths about the natural world, the world of bacteria and stars. It differs in a couple of respects from the ancient Greek practice. It relies on testing models through experiment and accepts axioms and explanations that are confined only to the natural world. You are likely quite familiar with the scientific method that is illustrated in the accompanying figure. It begins with noticing a pattern or asking a question, followed by the construction of a more general hypothesis to account for the observation. This is then tested with an experiment, and the results are analyzed and conclusions drawn. If the observations are consistent with the hypothesis, then one can more finely tune the hypothesis. But if the analysis and conclusions disconfirm the observations, then the hypothesis is false, and one has to modify the hypothesis and try it all over again, or reject the hypothesis outright. I'm going to illustrate the scientific method with a simple example. I recall from experience that a heavy stone hurts my foot more than a lighter stone when dropped on it from the same height. So I propose a general hypothesis that heavy objects fall faster than lighter objects. I now test this hypothesis through an experiment by looking for an outcome based on my initial observation or hypothesis. For example, I drop a heavy stone and a lighter stone from exactly the same height and watch which hits the ground first. If the predicted outcome is observed, the hypothesis is confirmed, and a more stringent test is proposed to tease out more of nature's secrets. If the predicted outcome is not observed, the hypothesis is either rejected or modified to account for the observation. In this example, I found that the two stones hit the ground at the same time, so far as I could tell. I must then abandon or amend my hypothesis. I chose to amend my hypothesis. When released from the same height, all stones will hit the ground at the same time. I redo the experiment with a number of stones, all with different masses, and dropped from a variety of heights. I observe that, as far as I can tell, they all hit the ground at the same time, so long as they're dropped from the same height. With the confirmation of the new hypothesis, I need to extend the hypothesis if I want to investigate nature at a deeper level. I propose the hypothesis that different objects, not just stones, will strike the ground at the same time when dropped from the same height. I then drop two different objects with the same mass, which I weighed in advance, a stone and a pillow, from the same height. I found that the stone invariably strikes the ground an instant before the pillow. My hypothesis is disconfirmed. At this point, it would be necessary to amend the hypothesis, say by taking into consideration the medium in which the objects are falling. I could perhaps, for example, drop objects in a container of water. However this investigation proceeds, it will likely result in a deeper understanding of nature. Now let's consider the most prominent figures of the scientific revolution: Copernicus, Kepler, Galilei, and Newton, in chronological order. First, Nicholas Copernicus. Copernicus was a Catholic canon in the early 16th century who is credited with launching the scientific revolution. He proposed a heliocentric universe in a publication called De Revolutionibus that was published posthumously. In his model, the Sun replaced Earth at the center of the universe, and Earth became the third planet revolving about the Sun. Today, we all know this to be true. Why then did many scholars remain skeptical of Copernicus's heliocentrism for more than a century afterward? Technically, it was because predictions of planetary positions were no better using Copernicus's model than the best geocentric models of the time. This was because Copernicus, like Aristotle, believed planetary orbits had to be circular. Direct evidence in favor of heliocentrism would not be found until the 18th and 19th centuries. What then led some prominent scientists to prefer heliocentrism before this evidence became available? Because Copernicus's model was far simpler and some would say more beautiful, more elegant than the rival geocentric models. Among the most important observations the heliocentric model explained was retrograde motion. For a more in-depth illustration of retrograde motion, see one of the modules involving stellarium. All planets move primarily west to east from night to night on the sky. On some occasions, however, a planet executes a retrograde loop, that is, moves east to west for some time before returning to its usual west to east prograde motion. The bottom left, you'll see geocentric models had to rely on planets moving in circles within circles as they revolve about Earth to explain retrograde motion. In the heliocentric panel, the bottom right, you'll see Earth overtake Mars, for example, which gives rise to this apparent retrograde motion with respect to the distant background stars. Next, Johannes Kepler. Kepler lived in the late 16th and early 17th centuries. He had a very hard life, and he had very eclectic interests, being a capable mathematician and made contributions to astronomy and physics. He also had a passion for astrology and numerology, but he is best known for his 3 laws of planetary motion. Using data of Mars that he obtained while working as an assistant to the last great geocentrist, Tycho Brahe, who was responsible for the most accurate naked-eye positions of celestial objects, Kepler discovered that planetary orbits are indeed ellipses and not perfect circles. Incredibly hard work over 20 years culminated in his 3 laws that you'll learn more about later in this course. Next, Galileo Galilei. Curiously, you all know this scientist by his first name, Galileo, rather than by his surname like almost every other scientist. Galileo is known as the great early 17th century experimenter capable of quantitative analyses who made fundamental contributions to many areas of the physical sciences, including astronomy. He is noted for using the newly discovered telescope to observe the moon's surface, sunspots, the 4 Galilean satellites of Jupiter, and for providing good evidence for heliocentrism by observing the phases of Venus. In the Ptolemaic geocentric model pictured on the bottom left, Venus will not exhibit full or gibbous phases. On the right, you see that Galileo did observe these phases using his telescope, which led him to support heliocentrism. In general, Galileo's observations paved the way for the theoretical work of Sir Isaac Newton. Galileo is also known as a martyr for science, according to the majority of science texts. What actually transpired is more complicated than the facile narrative that Galileo waged and won a war for science against the Catholic Church and religion in general. Historians of science have compiled over 20 myths associated with the so-called war between Galileo and the Church. They counsel that one should scrutinize carefully the narrative of any victor, particularly when the victor writes the textbooks. In the Middle Ages, church and state were inseparable. The Christian religion was not an enemy to science in principle. Its primary concern was the truth, after all. In practice, however, the church opposed challenges to its authority, particularly its interpretation of the Bible. This led to some unfortunate decisions on the church's part. Ultimately, the church learned to cede authority to science for descriptions of the natural world. Scientists also recognized that their authority was limited. Their investigations had to be confined to the natural world. Science could not address, for example, whether the supernatural existed or not. Einstein had the following to say with respect to the relationship between science and religion. Science without religion is lame. Religion without science is blind. Well said, as usual. And finally, Isaac Newton. It was the great Sir Isaac Newton in the late 17th century who revolutionized modern astronomy and physics with his 3 laws of motion and law of universal gravitation. Newton made fundamental contributions to mathematics and many other areas of physics and astronomy. He set the foundation for classical mechanics and the quantitative understanding of the motion of the planets around the sun and of the moon around the earth. Newton showed how Kepler's laws followed from his own laws. You will look more deeply into all these laws in your astronomy course. There is much history of astronomy between the time of Newton and today, but this is best left for individual investigation. There is one last point to raise, one last widespread myth to dispel associated with Copernicus. By the way, the image on your right shows a reconstruction of Copernicus's face based on a DNA reconstruction. Most scientists, even the greatest popularizers of science of our day, describe the Copernican revolution as a great humbling of humankind. After all, Copernicus dethroned Earth from its privileged position at the center of the universe, demoting it to the status of a third planet, right? It was science that put humankind on a trajectory of humility, a trajectory it has followed ever since. In fact, this is not quite true. The church well understood the difference between geography and morality. The church wrongly held Aristotle's position that Earth was at the geographical center of the universe. However, it also perceived the center as a morally inferior location, as, quote, the sump where the universe's filth collects. And so its repositioning as the third planet was actually a promotion, not a demotion of Earth and humankind. Science was therefore not the great humbling agent as often portrayed in astronomy texts and by popularizers of science. This concludes the History of Astronomy module.